Okay, now we can start this course fairly lightly by just giving you some simple introduction to what the control system is or control engineering. Now, control engineering as a subject is quite different from what people normally know. For example, if you study mechanical engineering, aeronautical engineering, or electrical engineering, or anything else, you know what you are probably signed up to. But control engineering is most time hidden inside of these subjects. In manufacturing, for example, that involves control engineering, robotics, aircraft, and so on. It is something that you don't come across very often or in a very obvious way, but it is used very widely in all sorts of industries. Now, I can give you some examples how the control is applied. Now, typically, when we refer to control engineering, we are talking about feedback control. Feedback control is a technology that relies on some kind of measurement, so you have a knowledge of what is happening. And cars is a good example. Cars nowadays, the car engines are managed by computers, and their fuel efficiency is much, much better than it used to be, compared with, for example, only 20 years ago. And efficiency of fuel is probably doubled. That's all thanks to the control, because it measures how the fuel is burned and it controls the mixture of air and petrol injected into the engine. Autopilots, nowadays, people can fly airplanes without the interference of pilots because it measures the height, it measures the speed, it measures the conditions outside, the wind, the weather, and so on. Robots, again, they rely on sensors and they rely on computers to actually find their way and to do whatever they are assigned to. If you work in a petroleum industry, then you will know things like flow, the pressure, the temperature control in a process plant is also rely on the feedback measurements, the control actions the computers take nowadays. So there's all sorts of control systems that if you look very carefully, you will see in different industries. But as a standalone discipline, people, with few exceptions, people don't go on and study an undergrad course in control engineering. There are examples, but very few. Now, I kept talking about feedback. Feedback is what you see, for example, here. And in the middle of this slide, you will see a process. If you look at the block diagram on the right-hand side, the object we want to control is called a process or the plant. And the plant has some kind of output, and that is measured through a sensor or a number of sensors. It sends back to the comparator and compare with what we would like this plant to happen. And that process is known as the feedback or the closed loop. You can see there is a closed loop happening. And the difference between what we want and what we measure is fed to the controller. Now the controller in the middle decides what to do for the plant. So you send a signal or for the process to take action so that the output, the actual output, will get too close to as much as possible to the input or the desired output. That process is known as the closed loop. Now, without that, you will have the first scenario where you have a process or the plant, and you have some kind of input mechanism that drives the process. And you just put in there input, say, this is what we want, but we have no control to what you will get from the plant. Now, partly because we don't know what that plant has to do. And partly also because the properties of the process or the plant can change over time. And as humans, we don't have 100% knowledge of that plant. So it's very difficult without the feedback control. It's very difficult to predict what you need to put input and to get what you want. So typically, that's why we need some kind of feedback. Now, when we talk about closed loop feedback, the diagram here in the middle is only a simple illustration of a closed loop system. And more often, for more complex systems, we will have multiple outputs, several different requirements or aims to achieve. We have multiple sensors that measure different quantities, and then we have comparators compare different requirements. So you have different inputs as well. Then you have several elements of the control or several aspects of control that looks after it. So you know what to tell the plant to do. So for feedback control, we typically classify them as single input and single output. That's the one in the middle, or multi-input and multi-output systems. Okay, but in this course, we will only deal with something simpler. That is the single input, single output, most of the time. Just to give you an example of feedback. So if you look at this diagram, what is happening here is we have a fluid tank, and there's a fluid comes in from the top, and there's fluid comes out there. Now the aim is to keep the volume of the fluid in the tank at a constant level. Now the fluid may come in at different speed. Okay, it doesn't have to be a constant flow rate. The fluid, you have to control the valve here, which is the actuator. That's a device that controls the actual action of your plant. You have the control there. So this guy there, and it just turns the valve, maybe open a little bit more or close it a bit more to control the output flow rate. Now, if I block that little window there, the guy doesn't have an idea what is happening. So there's no way you can actually find to know how much control you have over the valve. But because the guy has this access to directly, so he can see what is happening inside of the tank, so he can actually adjust this. So here we have the actuator, which is the device that controls the flow rate. Then there's his eyes, which act as sensor to detect the height of the fluid or the volume of the fluid. And then his brain act as a controller or as a computer to tell his arms or hands how much to turn or how much to close or how much to open. Now, of course, the control systems, most times they don't actually necessarily involve human beings. So this is another example, a fairly simple scheme, but similar of principle to the previous example. So what we have here is a tank with water comes in. Okay, so goes through here, but the water at the end of that pipe can be blocked by that little valve. The valve is controlled through this level, and at other side of this level there is a float. Okay, the float goes up and down according to the water level inside of that tank. Okay, of course, sometimes we can lose a little bit of water. That's still the steam coming out of the water. Sometimes the water level may change. Okay, so the float act as a sensor. The valve act as an actuator. So if the steam, when we lose water, the level comes down. The water level comes down, the float drops. When the float drops, that valve is open a little to let the water come in until the tank has enough water that as the float goes up again, that closes that lid. Okay, that is actually very similar, if you think about it, very similar to something we have at home. Have a think about that. What is that similar? Now, most of us probably drive. Now, driving a car is a multitasking job. Now, I have a block diagram here just to illustrate what is happening here. So we have a car here. We have measurements and different measurements, speed of car, the position of a car, and that kind of stuff. Measurements where I say they don't have to be the actual hardware device, but it could be your eyes and your body as well, so you can feel it. And the measurements is sent to this comparator and compare with what we would like that to do. Now you are, as a driver, is in control of a steering, for example. But you also are in control of the pedal. You can brake, you can accelerate. Okay, steering involves the job of following a road. Okay, so your eyes are the sensors. You know where your car is. So your hand are the actuators together with the steering mechanism. So you steer the car and you follow it. You follow the road. The road is bending to the left, and you steer towards the left. The road bends towards the right, and you steer towards the right. And that input is a road profile. You are required to follow the road, and the position of the car on the road is the actual output. Okay, so if you're not careful, you might end up in a ditch by the side of the road. And of course, you have to follow the road, but at the same time, you follow the road by adapting to road conditions. There might be a side wind that blew your car off, try to blow your car off the road, and you have to steer it back a little bit. Okay, that's called disturbances, the conditions outside your control, but you can actually control your plant, which is the car in this instance, according to outside conditions. Control of the speed is another aspect of driving a car. You stick to the speed limit, but you don't want to be too slow to hold up the traffic. And so you control the pedal to accelerate, you control the brake to decelerate according to road conditions. And also, the road may go up and down a little bit. So you go uphill, you have to accelerate. Well, put your foot on the accelerator pedal a little bit. If the road is going down, the car is going downhill, then you have to brake a little bit more. So there's all sorts of things that you need to control. And you might want to, for example, to consume fuel. So you want to sort of driving at a reasonable speed, you don't want to accelerate too fast, you don't want to brake too fast, that kind of stuff. So there's all sorts of objectives that you need to you need to be aware of, and you need to take control actions for. So these are the things, examples of it. Now, of course, again, driving a car nowadays doesn't have to be involved with humans. Autopilots nowadays fairly popular. A number of leading tech companies are actually trying to roll out these driverless cars. But driverless cars goes back, or the concept of driverless cars goes back perhaps at least 20, 30 years ago. This is probably one of the first driverless cars in the world. It was made by a research team at MIT, American. And now, of course, you can see quite obviously the technology then, 30 years ago, was not as advanced. So there are sensors, and you can see all the sorts of sensors on the car. They're not as compact as we have today. But there were in existence. The technology then, or the pioneer work at that time, actually paved the way for the driverless cars as we know today. Okay. We will have to, for this course, we will have to get used of this idea of using block diagrams, okay? Because it's one of the very useful tools that we use to study, analyze, and design our controllers. So this is just a typical of what we normally have. We have a plant or the process, which is an object for control. We have an actuator, which is actually a device that makes things to happen. Now, often we merge the two together. Okay, we merge the two and treat them as a single unit, or treat the actuator as part of the plant. And we take a measurement to what we want and send that back. And we compare that with what is required from the plant. And then the difference between what is required and what is actually happening is fed through this central device called control or controller. And this is really the focus of control engineering, how to design that controller to give you the best output, or the output as close to the input as possible. Okay. Of course, the design process involves a lot of knowledge of analysis of the plant. You need to know what the plant wants to do first. So you need a good knowledge of the plant. So the course will start from probably looking at the process to see what is the best to analyze in a theoretical way, to analyze a plant, and then how we can actually design the controller accordingly, according to different requirements. So typical objectives to design a controller. First of all, you have to stabilize the system. A system that is unstable, that goes out of control, is no good. Okay, so we need to make sure a system is stable, it is under control, it does what you want to do. We don't want a system where it has a mind of its own. It doesn't listen to what you want, the desired output. Okay, that's the first requirement. The stabilization is a very, very essential requirement for control engineering. We also, sometimes you have different objectives, as say, right, in some cases we may want the output to follow the input, but the input is a constant. It's a design set point. Okay, that kind of problem is known as a regulation problem. The input doesn't change, or change very little over time. Or, as your input might vary goes up and down quite a lot. And your output needs to follow that constant change input. That problem is known as tracking problem. But we also want to, in the meantime, whether it's recognition or tracking, we want the system to follow the input as much as possible, but do not respond to other disturbances, noises, as little as possible. The example I gave earlier about the driving a car has all the elements of that. Okay, we want the car to be stable. Okay, we don't want to sort of a car to follow a sinusoidal, for example, type of output. We want, if you drive on a motorway, you want to observe the speed limit, but get as close to it as possible. For example, in the UK, it's 70 miles per hour. So you want to drive your car at that speed. That's a regulation problem. But you want your car to that speed, regardless what outside condition is. Up and down the hills, wind, you have headwind or tailwind, things like that. These are the disturbances to your car. Okay, so you want driving a car at a constant speed of regulation, but you want your car to keep to that speed despite all the disturbances from outside. Following a road is a tracking problem because you have the road profile changes. You go drive around a bend, you drive around a street corner, and you have to follow that. So the road conditions change as well. Okay, you might have side winds, you might have narrow roads, you might have to change lanes from one side to another. So, and these are the disturbances, but you have to follow the profiles. So this is very light touch for the first session, and I like to think about possible examples of real-life experience where the idea of feedback is applied, and explain how feedback in these examples may work. Just have a think. Okay, it's fairly light touch. I'll come back for the next session. Thank you.